Hi. Hi everyone. Thanks for coming. I'll talk here today about Stwo and the future of Starknet scalability, and hopefully these words will be meaningful by some part of the talk. All good? Okay. Sorry about that. First we'll talk a little bit about what Starknet is, then we'll talk about what Stwo is. Stwo is our next-gen prover. This is the main part of the talk. Hopefully we'll understand why you need a prover for Starknet at this point. And then we'll talk a little bit about how this relates to Starknet's privacy roadmap and what we want to be doing in the future. Raise of hands, who knows Starknet? Okay. And who knows about zk-rollups? Okay, so most of everyone, so I'll keep that short. So Starknet is a zk-rollup over Ethereum. It's the first zk-rollup. It's the most performant zk-rollup, and it's the first one to also be stage 1. And what does this mean? It means that it is a blockchain. Just like Ethereum, there are blocks, there's transactions in blocks. It operates differently, but the idea is the same. And every block, as opposed to in Ethereum, where a block is verified by validators and the entire network re-executing transactions to verify the state, in Starknet, each block is proven. What does this mean, that is proven? It means that the execution of the block is translated into a trace, which is we can think of it as a mathematical statement. And this mathematical statement is proven, and a proof is written to the Ethereum blockchain and to a smart contract that verifies this proof. And then all of the Ethereum validators run this smart contract because they re-execute everything. And this way, the state of Starknet is verified. So Starknet enjoys all of the security of Ethereum without the need to re-execute every block. So this, of course, only makes sense when proving and verifying are cheaper than re-executing, right? Because otherwise, it would make sense for everyone on the Starknet network to just re-execute everything. But we want it to be cheaper and faster and more performant. So the purpose is to greatly increase by orders of magnitude what type of computation you can do on a blockchain, enjoy the same security of Ethereum, and utilize proving. And soon, Starknet will also be hopefully a zk-rollup over Bitcoin. So it will enjoy not only the security that comes from Ethereum proof of stake, but also from Bitcoin proof of work. And also will enhance what you can do with Bitcoin, bringing DeFi and other opportunities to Bitcoin. So, okay. I think this is an old version of the slides. Okay, so what is Stwo? So we said that proving and verifying need to be performant enough for all of this to make sense. Currently, Starknet runs with the Stone prover. Stone, Starknet 1. And now we're moving to Stwo, Starknet 2, which is a new prover. So Stone is based on Stark technology, Starknet. And Stwo is meant to increase the performance and of proving greatly. So how is this done? Stone was developed to make verification super cheap. And it really is pretty cheap. It runs in production on top of Ethereum for years, and there's no problem verifying the proofs. However, Stone is not as fast at proving because we aim to have fast verification. Now that things are stable enough, we've been live long enough, we want to optimize for proving. Because the proving also has to be cheap enough to scale to the extent that we want to. So this is why we came up with Stwo, the great people at StarkWare. It's based on circle Stark technology, so this is very beautiful math, which allows the Stark-like protocol to exist over a small field, small finite field. So Stone operated over a pretty large field, but Stwo operates over the Mersenne field, which is 2 to the 31. And there's very, very nice math behind it. I left some links at the end of the slides if anybody wants to read about how this works. But basically, the idea is to find a field that is small, but also has a large multiplicative subgroup. And this happens to be the unit circle in the Mersenne field. And so this allows us to utilize fast arithmetics that come from the small field, but also enjoy all of the properties that we need for folding and the stir-fry protocols, so everything kind of magically works in this construction. So very nice if you're interested in that. Stwo also utilizes a flat air design. What does this mean? So proving time scales linearly with the number of rows in a trace. So remember, when you execute a program in Cairo or anywhere, you can translate this into a trace, and this trace is then interpreted as a set of polynomials. So so you have this trace, it's a table, think of it as a table. The more rows you have, the slower the prover. The more columns you have, the slower the verifier. Stone optimized for many rows and a few columns to have fast verification. Stwo optimizes for fewer rows at the expense of columns. Not too bad for verification, but this is, you can think about it when you look at actually how the errors are written, how this translation to the trace is done. It kind of looks like one-liners in Python, where you kind of have lambda functions. So this enables the trace to be kind of squashed and flat. So this brings a lot of performance to Stwo. And also, Stwo, it's not written here, but Stwo has a very nice property where each opcode is a different trace element, and you don't need to pad the trace to the nearest power of 2, which also brings a very big performance boost compared to Stone and to competitors. So we saw that the SP1 posted about them doing this. This already exists in Stwo. So it's very, very performant, and I have some benchmarks to show you. Something happened to the slides, sorry about that. So all of these benchmarks that I'm going to show, Stwo is benchmarked on Cairo 0 code, so just Cairo code. So it's a general purpose prover. You can prove any code, just proven in Cairo. And we compared against competitors in Rust, but also against precompiles. So these are benchmarks for SHA-2. And we see increasingly growing targets, and you can see that Stwo beats the competitors with Cairo codes even when compared to precompiles. So that's how performant Stwo is. You can see that on Cairo 0 code, it beats SP1 and RISC-0 precompiles, not even talking about Rust. Also, on SHA-3 chains, Ketchucks, so we have 32-bit Ketchucks, and these are running for increasingly long chains, so just recursively hashing. And you can see again that Stwo outperforms SP1 and RISC-0 precompiles with Cairo 0 code by a factor of like 30 to 40. So this is even without writing dedicated errors for Stwo for these targets that we probably will do at some point. Okay, so skipping a little bit. Okay, so what is the roadmap for Stwo? Stwo currently proves Cairo code. We are aiming to implement a variant of Cairo called Cairo M31, which basically restricts Cairo to the small field. We expect this to give a performance boost of between 10 to 50x over the benchmarks that you just saw. So hopefully this will be coming soon. Also, we are working very hard on implementing a GPU functionality for Stwo, which also should drive up performance by quite a bit. So this should be coming within this year, I think. Also, there are already RISC-V errors for Stwo developed by Nexus, the Nexus team. And we aim to enhance those and build upon this so people can, if they want, prove Rust with Stwo. But the main purpose that we developed Stwo is to decentralize Starknet. So we are committed to making Starknet the most decentralized zk-rollup. This means that it will be decentralized not only in sequencing, which is coming soon, but also in proving. So we want to make Stwo so fast that it can prove the Starknet state. It will be cheap enough to prove the Starknet state that we can really decentralize proving. Because we don't want to be in control of proving the network, we really want to decentralize it. And additionally, we want the bonus of having people be able to prove things on client side. So proving claims on end devices, for instance, for privacy, private payments. We know this is a kind of a painful spot for blockchains. Hopefully, by utilizing Stwo, you could have private payments in your mobile device. AI use cases, so provable AI is becoming a hot topic. We hope Stwo, we have some benchmarks on matrix multiplication, and we have the Giza team implementing errors for AI purposes for Stwo, and zk identity, verifiable credentials, all of this. We want to make Stwo the default for all of these use cases. It is the fastest and best, and we want to drive this even further. Stwo is fully open source. You can play around with it now. We also will build a lot of dev tools for it, so you can just easily utilize it for your code. So Stwo and the ecosystem. We're going to, so the Kakarot team are working hard on real-time proving of Ethereum blocks with Stwo. And we hope that this will happen sooner than later. As I said, we want to be a zk-rollup over Ethereum. Stwo is the driver of this because the Starknet state would have to be verified using Bitcoin script. We are making a push in that direction. Layer 3s, so blockchains on top of Starknet could settle their state to Starknet using Stwo. As well as any other blockchain that would want to settle their state to Starknet. And that's it. So, as I said, this kind of all coincides with privacy. So, at Starknet, we want to be a home for privacy applications. And we have several ways that we want to drive this. So the first and foremost, I would say, is that we want to make Stwo the first truly zk prover. So currently, zk Stark prover. So currently, Snark provers are pretty naturally zk, but Stark provers are typically not zk. They offer typically sufficient privacy for all use cases that you can think of, but to be truly zk would be nice, and we hope to make that happen in the next year. We are making a big push to be the home for private compliant payments. So bringing cheap, fast, scalable, compliant payments to Starknet is really a goal for us. So anyone interested in building anything like that, Stwo, we hope to make the home for that. And also, Starknet is a very cheap home for verifying snark proofs. So we have an ongoing collaboration with Aztec and Noir to bring Noir developers to Starknet. So you are very welcome to write your code in Noir, and you can automatically generate a Starknet on-chain verifier for your Noir program, and have privacy on Starknet basically for free doing that. Free coding-wise, not free transaction fee-wise, but very cheap transaction fee-wise. And that's part of our goal to be truly decentralized in the technological stack, proving stack, sequencing stack. So that's where we're going. And here are some resources. So you can go to the Stwo and Stwo-Cairo repos, and Stwo-Cairo has actually examples that you can run, and you can write code and prove it locally with Stwo. And there's a link to Nexus and their RISC-V efforts, and some GPU resources. And if you want to read about the very beautiful math behind CircleStark, there's a couple of blog posts here by ZK Security, and I think they're amazing. They're the best ones I've had the chance to read. Yeah, so thank you.
We've got about 10 minutes for questions, so quite enough time, so feel free to ask, guys. The microphone is just here. Raise your hand if you want to ask a question.
I saw some topics about the AI, but you never mentioned. Can you explain me more about the topics? That how can Starknet will be achieving some AI or? Okay,
so first of all, Stwo is a good choice for proving AI. Anything related to, I think a really interesting use case is to verify the authenticity of photos, or how a photo was maybe edited, or video. So maybe you take a photo and you want to make sure, you want to prove that the only editing you did is cropping. So you write your editing software in Cairo, and you prove with Stwo. You have a signature from your device that you took the photo with the device where and when you said, and then you crop it with a Cairo-based photo editor, and then you generate a proof because it is a general Cairo code, so you can just prove it on this input, and then you have a proof that you didn't edit the photo other than cropping it. Same goes for video authenticity, anything like that. Agents in blockchains are a hot topic now, so anything like that. Giza are working on this. They already have some implementation of this going, and they're also working on like deep learning type of things. So I think this is really an area to be explored, because we're at a time that really AI is generating most of what we see, and at least if you know what kind of AI or model was used on what input to generate what output, this is a lot of power that we currently don't have. Like watermarking techniques for AI are very weak at this moment, so I think this is a promising direction.
Yeah, another question is Plonky 3 also integrates M31 as a possible field for the proof. So my question is, does CircleStark only replace the field using quadratic extension to restore primitive roots of unity, or is there a specificity in the CircleStark that has a different functioning and different efficiency than the one used in Plonky 3?
So the efficiency of Stwo stems from several different things that we did. The first one being utilizing the Mersenne field with CircleStarks. There, the complexity was to understand how the math works, right? So you have to, basically for, the hard thing to do is the folding that you need for fry and stir, right? The kind of like what you do with our RSA and FFT. So you needed to find this multiplicative subgroup of large order, and you needed to prove that you can both have this coset that you can move, and you can fold, and you can half the number of half the size of the polynomial, basically. So this anyone can utilize with any prover if they utilize CircleStarks correctly. We have. But this is open source, anyone can do it. But I think where StarkWare's implementation really shines is also in the air design. So writing airs is kind of a very specialized field, and you need to take the opcodes of your virtual machine. If for us this is a Cairo virtual machine, it's optimized for proving, but also for RISC-V, and you need to translate these operations of the virtual machines into arithmetic representation. This is what you call AIRS, arithmetic intermediary representation. And you really want these AIRS to be as succinct as possible, and this is kind of a specialty, and this is most of what we have done with Stwo. So writing the initial CircleStark implementation, like coming up with it was hard, but the implementation was not the majority of what we took to make Stwo happen. So writing errors efficiently is kind of a very specialist task, especially when you try to minimize the number of rows at the expense of the columns. You need still reasonable verification. So this is what I was talking about the flat error design. This is a major change. And also getting rid of the padding was another engineering effort. So kind of there's a lot of things to do. There's still room to improve. People are doing weird protocol. People are doing multi-variant polynomials. There's still ways probably you can push this. And we are still doing that as well. But so it's not just a matter of implementing circle starks. You really need to work on a lot of things to push the performance.
Hi, how's it going? Thanks for presentation. Yes. This is Dieter from Web3Wiz, and I wanted to ask you about an application. So what we do is we offer websites widgets that they can embed on their website to like interact with crypto. And we also saw the Gnosis hack that was focused on front end. So I was wondering if there is a way to use these proofs to prove the front end of blockchain applications, and if you could give me at least a high-level picture conceptually how it would work. Thank you.
Yeah, so currently Stwo is WASM compatible. We're working on pushing the performance a bit. So technically, yes, anything with WebAssembly you can use Stwo to prove. And you would write your front end with Cairo, or a faster variant of Cairo, the Cairo M31 when it's out. And you would need to, like, once probably the user inputs their input to whatever they need the functionality, you create a zero-knowledge proof that this is the code that ran on your website, and that's it, you have a proof, and then you can utilize it for whatever you want. You can go on-chain, you can go off-chain. Yeah. I hope that answers your question. Yeah.
Yeah, thank you. Can you elaborate a little bit about decentralization? Did you mean to add more sequencers, or did you mean something else? Thank you.
So we are both adding more sequencers. So the next version of Starknet will have all of the code to decentralize the sequencer, and we will run several sequencers locally just to make sure that everything works the way it should. And the hope is that in the following version, or the one after that, we will open sequencing up to anyone. We also want to reduce the cost of running a sequencer, because currently it's quite expensive. We want it to be cheap enough to be viable for users. But we also want to decentralize proving. So in Starknet, you need to sequence it, but you also need to prove every block. And we don't want to be a centralized proving service. We want competition there. We want, especially for liveness, right? You don't want to have only one organization in charge of this. So we aim to make this cheap enough and achievable for anyone that wants to.
I have one question concerning RAM usage, and this might be a new question because I actually don't know. But is the fact that some Stark protocols are high in RAM usage, is it inherent to Stark, or is it just a byproduct of not optimizing for low RAM usage? I'm asking because of client-side proving in the future.
I don't know if it's a Stark thing, because when we benchmark against Jolt, they run out of memory a lot sooner than we do on CPU. So they're Snark-based, so I don't think it's an inherent Stark problem. It's not something that we optimized for a lot, but for Stwo, but it is much faster even for like less RAM than competitors, I think, but they're also Stark-based. So the short answer is I don't know if it's a Stark thing. Yeah.
One more last question, if anyone has any. Otherwise, we're ready to move.